Okay, going a little out of order here, we're skipping to section 5.5. That's okay. Doing this because in this section, what we see up here, indefinite integrals and substitution method, this is one of the really critical sections moving forward into Calculus 2. So I wanted to do this before the very end of the course so that we have the time to really fundamentally understand this concept, so when you move forward into Calculus 2, hopefully you know this. And it also works very well coming off of what we did with antiderivatives in the previous section. Remember, antiderivatives and indefinite integrals are the same thing. And so what we'll be learning in this section is one of the first techniques of integration. One of the things we said in the last section was that integration, antidifferentiation, was going to be harder than differentiation. In differentiation, when you had products and quotients, you either had to simplify them away or use the product and quotient rule, product rule or quotient rule. That's not the only options in integration. In integration, when you have products and quotients, first you will try to simplify. Then if you can't simplify them, you will then have a host of other things from which you will choose. And not all of them will work. And so you'll spend a lot of time in Calculus 2 looking at a problem and say, oh, this is a problem that has this format, I should choose this technique. And so what we'll be doing in this section here, 5.5, is one of our first techniques. And it's not going to work for all, and it's going to be mostly products and compositions here. It's not going to work for all products and compositions, but it'll work for some. And it's one of the fundamental techniques that you hopefully know, so that when you go to Calculus 2, you will be able to use it well in Calculus 2. But it's one of our first techniques of integration, because integration is going to be so much harder than differentiation. There is not going to be a product rule for integrals. There is not going to be a quotient rule for integrals. There is not going to be a chain rule for integrals. There's going to be a bunch of different things that you can try, and generally only one of those different things will work. Generally. Sometimes more than one will work, but a lot of times it's just one. Now, fundamental to when we learn this new thing called the substitution method is remembering the things you already know. So from last section, we learned all these basic integral forms. And it's really, really important to know these basic integral forms, because what the substitution method is going to do is hopefully take a form that does not look like one of these forms and change it into one of these forms. And then once you see one of these forms, you should know the answer. So these are all the basic forms that we learned in the last section. You still need to know them. So that being said, let's look at this first problem. Now there's nothing special about this first problem, but we would note that this is a product / composition. And remember, the concept of composition is a function inside a function, that I have that x squared plus 3 inside that square. And this can pretty much easily simplify. So that's what I am going to do. I'm going to go ahead and simplify this first. And anytime I can simplify my original problem, that's the choice I'm going to make. So I can FOIL that guy out there and get x to the 4th plus 6x squared plus 9 dx. And then I could distribute that 2x and get 2x to the 5th plus 12x cubed plus 18x squared. And now it's not a product, it's not a composition, so I can just use my basic rules. Pretty much increase the exponent by 1, multiply by the reciprocal of the new exponent. Increase the exponent by 1, multiply by the reciprocal of the new exponent. increase the exponent by 1, multiply by the reciprocal of the new exponent, with my coefficients just kind of hanging out. And so final answer, 1/3 x to the 6th plus 3x to the 4th plus 6x cubed plus c. And there I did it without much fuss. But point here, it was a product / composition. I acknowledged that by simplifying it away. I just didn't work with each factor independently, because that's completely wrong, and you will lose all the points if you do that. But I went ahead and simplified it first. Then I was able to integrate it. And remember, the integral sign in the differential dx, that is your notation that says integrate now. And then once I find the antiderivative, once I find the indefinite integral, then I drop both the integral sign and the dx. It's not that they disappeared. I did what they said to do. They said find the antiderivative. I found the antiderivative. I stick on my constant of integration, and there's my answer. Now remember, you can check this answer by differentiating, but it's only going to take you back to this spot right here. It's not going to check your algebra. Okay, so there's the first guy. I probably spent way too much time doing a relatively simple problem. Now, again here, we chose to simplify because it was easy to simplify. Compare that problem to this guy here. So all I did was put a 0 after that too. It's now an exponent of 20, and you aren't going to multiply that guy out. It's not realistic. And so simplification, not really an option here. And so we note that it's a product of composition that cannot easily be simplified. For many problems like this, and also quotients in compositions, we will integrate by using substitution. This method is commonly known as U substitution. Some basic steps, the substitution rule, the substitution method. Here's what mathematicians give us. If u equals g of x is a differentiable function whose range is an interval I and f of x is continuous in I, then the integral of f of g of x, g prime of x dx equals f of u du. That's all the mathematicians give us. But it does give us an idea of the form that we're looking at. There's my form, that the form is a composition and the derivative of the inside. Right? Composition, f of g of x, composition, that idea of one function inside the other, followed by g prime of x, the derivative of the inside. That's my form that they said to look for. A composition and the derivative of the inside. Now that's very general. We will be able to tweak it a little bit, that maybe you won't have to see the entire derivative of the inside, but that's the form that this is suggesting we look for to try this thing called a U substitution. Okay, so some basic steps. 1, choose U. Try one of the following. Note the list below is not to be a complete list. This is just a list of the most common choices in this class. U equal the inside function, because we're going to have that composition thing. U equals something to create the form 1 over u du, which integrates to the natural log of u. I probably should have absolute value around that. And again, when we talked about this in the last section, I'm not going to get really upset if you don't put the natural log around there, but there probably really should be natural log of the absolute value of u. Or I said put the natural log in there. The natural log is really important. So I was talking that there really should be absolute value there. It really should say natural log of the absolute value of u. But if you don't put the absolute value, I'm not going to be terribly upset about that. And as far as the computer, if the computer wants absolute value around that u, put absolute value around it. C, u equals something to create the form 1 over a squared minus u, 1 over the square root of a squared minus u squared du, which integrates to sine inverse u over a plus c. U equals something to create the form 1 over a squared plus u squared du, which integrates to 1 over a tan inverse u over a plus c. If an exponential function is involved, try u equal the exponent. And then F, because we don't yet know how to integrate the natural log of x, sine inverse of x, or tan inverse of x. If one of the previously mentioned functions is present, let u equal that function. Now that is something that's definitely not going to be an always. Unfortunately, in calculus, well, calculus 1 here, and then when you go into calculus 2 and you learn to integrate, there is never going to be an always of what you should do. This is just a suggestion right now that if you see natural log of x, sine inverse of x, tan inverse of x, maybe letting u equal one of those will work. Maybe in the future it won't. There is never going to be an always when it comes to integration. 2, calculate the differential du. We'll practice that step momentarily. 3, solve for dx. 4, using u and dx, substitute into the original integrand, resulting in new integrand in terms of u. 5, if the integral is not entirely in terms of u, try to solve for x and substitute again. If this is not reasonable, stop. You cannot proceed if the integral is in terms of 2 variables. Except for when we did implicit differentiation, related rates, this is single variable calculus. So after you do the substitution, if you still have 2 variables, something's going wrong. Stop. 6, integrate. 7, substitute back to the original variable. 8, check by differentiation. That's an optional step, but a good step. But what we're going to do first is we're going to practice step 2 here, calculating the differential. And that's not hard. So let's give a definition of the differential first. Let u equal f of x be a differentiable function. The differential dx is an independent variable, and the differential du is given by du equals f prime of x. And so this is just telling me what the form of du is. It's du, a derivative dx, that you're just working on whatever function you have, or whatever equation you're given. So for each of the following, calculate the differential du. In my form here, the form every time is going to be du derivative dx. Just using that equation up there. So in this case, du, derivative of sine is cosine. My angle doesn't change. Chain rule times the derivative of the inside, so times 3 dx. And there we calculated du. Same thing on this one. Again, your form is du equal my derivative dx. So in this case, du, then the derivative of this, 1 over the argument, derivative of the argument, dx, or du equals 2x over x squared plus 1 dx. That's all there is to calculating the differential, just knowing this form and then just taking a basic derivative. So we will end this video, and in the next video we will start this thing called a u substitution.